In this experiment, we will demonstrate that white light is composed of all visible wavelengths through diffraction. As you may recall from the double and single slit experiment, light will interfere and create points of constructive and destructive interference when passed through a slit, called an interference pattern. Similar to a single or double slit, light will diffract and interfere when passed through a diffraction grating. A diffraction grating is a series of very many tiny slits that are so close together you can't see them without a microscope. However, because there are hundreds of slits so close together, the interference peaks are very sharp. Interference peaks of lower wavelengths are closer together, while longer wavelengths are farther apart. Because of this, different colors will line up at different points on the spectrum. Blue light should be closer together than either green or red light, just like we see with a single or double slit. This video will show how to do Activity 5 and how to interpret the results. For the activity, we will record the spectrum spread out on a piece of paper. Mark the white line of light with a black marker. This will be your center point of reference. When you turn off the lights, you can see that the light has diffracted and spread into a spectrum on either side. Take a blue marker and draw a line where the blue light appears on both sides. Do the same for green and red light. Notice that the blue lines of light are closest to the center, while the red lines are farthest from the center. Green lines are found in between. This is consistent with the diffraction patterns we saw with the double and single slits. This is also consistent with the interference we saw in the ripple tank. Diffraction also works in light beyond the visible spectrum. Ultraviolet light is right next to purple and blue light in the color spectrum, but outside the visible range. UV has a wavelength just shorter than purple light, so it should appear closer together than the visible light we have explored. We can confirm this by completing another similar experiment with a UV light. Using the original setup and a purple marker, we first mark lines where we see purple peaks. With a 365 nanometer flashlight and some neon fluorescent paint or tape, we can see where UV light appears compared to the visible light spectrum. After applying some fluorescent paint to the ring and switching to the UV flashlight, we can see the UV light diffracted on the paper strip when the lights are turned off. We then mark the peaks of UV light with a black marker. When hit with UV light, the paint reflects light of a visible wavelength and glows, which helps us see the interference peaks. Without this aid, the UV light is very hard to see. This is because the UV light is on the very edge of the light we are able to see. After turning on the lights, we can see that the UV light appears right next to the purple line and extends where we can no longer see it with our own eyes. Compare these lines to the lines you saw with the visible spectrum.